Hello and welcome to Terminal House Media. I'm the operator, and tonight I am going to be going through a little bit of documentation, reviewing my environment. I'm also going to be adding to my environment. I am streaming very late tonight simply because I worked very hard on updating some documentation for you and to better help me understand high performance computing. Why use high performance computing? Because it performs well. Obviously, it's in the name. It's high performance. So I am running worker node 01 through 03 as stateless virtual machines. So that means they are running their OS in memory, and I am managing that through my management server MGMT01. What I am going to do today is add storage, hopefully, to my environment. That's the overall goal. Here, I have written up some documentation, and we can go through this. And it's simply why high performance computing. Let's correct this. Did I write up this information? I spoke my idea into ChatGPT, and then it helped me write this. Okay. Anyways, why high performance computing? High performance computing helps people solve problems that are too large, complex, or time sensitive for ordinary computers. What is high performance computing? High performance computing is the use of many powerful computing resources working together to solve problems faster and at a larger scale than a typical computer can handle. Why this guide exists, why I created this. I am studying high performance computing to build a deeper understanding, contribute useful knowledge to the community. And you'll see why I say that. And that's no shade. It's just, I don't know. I have no idea. Nevertheless, you'll see why. And then, and evolve my technical abilities. This guide documents that process openly and is not presented as the final word on HPC, but as a structured journey through the technologies and concepts and responsibilities that make these systems work. The original HPC architecture. My understanding began with HPC reference architecture, NIST SP 800-223. So I'm going to copy this. Really, my understanding kind of began with a YouTube search. And learning about AI well before the curve. But this is the best way to put this into words. And I came across this information as well. But this was recently brought back up to me. I never read through it. But then I read through it this week. And so it's pretty interesting. But when they get to the zones and topology, boy, I've seen this for years, and I don't know why. A lot of it didn't really click, maybe because I didn't read the documentation. But nevertheless, it does click now. But I also still think that, like, looking at it like this, it's you know what? I just noticed. Anyways, this is like my 1,000th time looking at it. I've been looking at this for weeks. These are servers. That's why it looks like this. So this is the stack, how it looks over here. And this is the stack, how it looks over here. You got the compute, then the storage, and look at all the drives. Wow. It took me this long for it to finally click to see what I'm looking at. Nevertheless, I spent the whole evening working on this documentation because this didn't make sense to me, and now it makes sense to me. That's crazy. I mean, maybe it makes sense to me because I drew the whole thing. All right, let's keep on going. That is wild. So we go back to this tab, and right, so I don't know. I've been introduced to AI and supercomputing for a while, so I've been interested, but I've been shown and heard of this guide some years back. Never really went through it. And then really went through it this past week here, and yeah, cool. But anyways, 5, understanding the building. This building, which you'll see in a second, is a visual model of an HPC environment inspired by the Indiana-Michigan Power Center in Fort Wayne, Indiana. I chose it because HPC delivers the computing power needed for many major scientific discoveries and technological breakthroughs. Each zone represents a major layer of the system, including its hardware, software, services, and people. The zones do not represent the exact supercomputer, but provide a simplified framework for understanding how an HPC environment connects and functions. And I guess maybe this is to compare. This is how, I guess this building is how I think of tunneling through a network, right? That would be more of what this approach is. And this image here is literally if you go into a data center and you see an HPC or HPC high performance HPC system, right? You're going to see the login nodes and the data transfer node and the web portal on this stack. And probably these are the, 1U servers and, or those 2Us. I can't tell if that's indicating 1 or 2. No, because this looks like a 4U right here. So maybe these are 2Us. But you got these servers and be on the left side, and then you got these servers be on the right side, or maybe they're split across on another side of the, I don't know, who knows how it is, but it could be different for different people. But I can really see how this is a rack to the left, rack to the right, and then we go to my breakdown of what I was doing. And right, Indiana, Michigan provides power and takes a lot of money from people. That's their point. Well, anyways, so the first zone you have as an access zone, and the second zone would be the management zone. The third zone would be compute zone, and the fourth zone would be the storage zone. So I look at it like, you've maybe, I guess that's where the other part comes in. So go ahead and go over to focus real quick. So today, for you all, I was also working on a little video this evening that maybe hopefully I'll be able to post. I don't know, kind of taking my time on it, but I'm gonna add a source to this video. Application. Okay, here we go. Gonna capture this window real quick. Okay, and Where did that just go? Oh, there we go. Okay, so let's put this here. Transform, fit to screen. All right, so we've got this little video that I kind of thought of with AI and whatnot. I don't know, but so let's just go through just do a little storyboard. You're on a plane, you're flying in, you're doing something important, you're really cool. All right, you're on the plane, your buddies are watching the game and everything, and you're really important, you're really smart. For whatever reason, you're really, really smart. Cool. Oh, that game looks really cool. Look at that plane. That's a nice plane. Very nice plane. Oh, I'm looking in my bag. I need something. What do I need? What do I need? I really need something. Oh, you can't see this. Wow. How much of a horrible... Anyways, let's see. Let me edit the properties. Capture. Let's go with Windows. Okay, now you can see it. So we're going to narrate that one more time. All right. I'm on a plane. I'm on a plane. I'm on a fancy plane. Private plane. It's got my logo on it. I'm special. Look at me, my buddies. We're watching a basketball game on the plane. We're smart. We're special. Wow. They're dribbling the ball. Look at the people in the crowd. They're having so much fun. Everybody's having fun. Look at everybody looking up. Oh. Are they going to score? Oh. We don't know. We shall never know. But we are in a plane and we're flying. We're having fun. We're going. We're doing things. Cut. I'm looking in my bag. I need something. What do I need? Oh, I'm bored of you guys. I'm obviously not watching the game, so I think I need my phone. Where's my phone? Ah, there it is. I love being on my phone. Oh, look at that. Is that an alley-oop? Oh, they missed it. And I also missed it. I wasn't even watching. Oh, there's a news broadcast. What's on the news? Let's find out.
Breaking news. High-performance computing drives today's agenda as the race to secure tomorrow's technology intensifies.
Oh,
live
really?
from Washington.
Wow. I didn't know that. Oh, boy. I've got something to do. I got something very important to do. What am I got to do? Oh, I'm going to land on top of this building, and I'm going to gain access into the Indiana-Michigan Power Building. No, I'm going to gain access into high-performance compute. And I'm going to enter the access zone. Into the access zone I go. All right. That was my fun thing. All right. So now we're at the access zone. And in the access zone, we can do a couple of things. Let me go ahead and pull up those notes. All right. I'm going to go with white. And in the access zone, we have our login nodes. Data transfer. And there's one more thing. I've got plenty of notes to go through to make sure this is accurate. Procreate. The web portal. And web portal. So the web portal is something that I actually want to work on tonight. And then the login nodes and the data transfer I use as the management node. And then we've got the management zone, which, okay, you know what? I'm gonna do a Bastion node. Man, I'm running out of virtual memory and virtual space really on this server. So that's 3 more virtual machines. Anyways, I guess I could do it with 2 more virtual machines. All right, so management zone. Let me see. We got provisioners and schedulers. And then we've got schedulers. Now, for schedulers, we've got Slurm, is what I'm going to work on in my stack. And provisioners, I'm going to do Lustre, single node, and Weka containerized. And then let's see. So I'm scrolling down. We got zone 3, which is compute zone. And for me, it's going to be bridged. I'm going to be using my B-Link SER 9 and in production environment you use enterprise compute hardware. And then we have the storage zone. Wait a minute. Provisioners. I did that wrong. Provisioners, I put my storage solutions. Oops. All right, so my provisioner, I'm actually, man. So you got Warewulf, which is, you've been seeing that a lot, and all the hints to that. Then, boy, oh boy, there are quite a few provisioners. That's a, you got Warewulf, Bright, Omnia, PBS, Open PBS. And the question may be, why so many? But Warewulf, PBS, and Sprite, I think. Those are the 3 that interest me the most. All right, and then I need to learn some more schedulers. I guess PBS works as a scheduler as well. we're gonna check all this stuff out in the lab. Oh my god, once again, you guys can't see anything. I'm just focused in on my screen. Well, this is a horrible stream with no concurrent viewers, so that's all right. But sorry about that. Hopefully we can fix that. But this is what I've got going on. We've got our high performance compute. This represents, I guess this is a building, but it also kind of represents a server, if everything could fit in one rack. But we've got our login nodes, the data transfer, and the web portal. We got the provisioners, Warewulf, PBS, Bright. We got our schedulers, Slurm, and PBS. And for me, in my environment, for what I want to learn, I'm going to be using my B-Link SER9. Let's do this. All right. See something real quick. Chat. Properties. All right. So just wanted to make sure the chat was up there, even if no one comes in. At least it's there, it's available. All right. So then zone 4 for storage, like I said, I kind of messed that up earlier. That's gonna be Weka and Lustre. I'm going to be doing Weka containerized. Gross. All right. Lustre. All right. And that's the building. Yay. Super tall. Cool. We did a good job. All right. So all right. I think that was a pretty good overview. So if we go over to, that was a horrible overview. I'm sorry for anybody. I'm sorry about that. I'm going to get better at managing this OBS. There's a lot to manage. All right, but so I've got my management server, I've got my worker node 01, worker node 02, worker node 03. And let's see. Let's open up Claude real quick. Which is the more memory and CPU demanding storage solution for PFS, parallel file systems? Lustre lowest, but not really a parallel file system. The same league. Lustre FS lower, not a dedicated metadata server. Uses elastic caching, simpler. Modern design to be leaner and less than Lustre BGFS. Lustre Ceph, no special kernel patching required. Reasonable memory. Footprint on metadata, storage servers. Good middle ground for lab. Lustre, moderate heavy, but different shape, lighter node running Ceph, but the MDS metadata server can get memory hungry with large numbers of small files. So I think what I wanted to do was do Lustre. They didn't mention Weka. I was looking a lot of this stuff up earlier using Gemini. So what I believe what I'm gonna do is run, like just like my note says, run Weka containerized and Lustre on a VM. I want to run Weka containerized and Lustre on a single VM. Want to run Weka containerized on a host VM and Lustre on a single VM. That was a horrible sentence, but whatever, we're gonna roll with it. It'll understand it. Hopefully you all do too. Let me, while that's doing that pull up, so I can go to Hornet's Nest and we can see CPU. I've got some space left, quite a bit, but I don't want to get too greedy with what I provision out. And memory, I'm great. I think that I can do a little bit with what I want on there. Now this hard drive space that's available is kind of making me question, because let me go to system. Okay, there we go. We got plenty of space left. I was gonna say. So we're gonna create 2 more virtual machines, I believe. Pull back up Claude, see what it says. Both are doable, but they slit at very different levels of lab friendly. Weka containerized on a host VM. Weka isn't open source. You'll need a trial account. Absolutely not doing that. Lustre on a single VM, more standard, more useful for actual learning PFS internals. Combined MGS, MDT, OST on one node is the well-trotted all-in-one test config. 2 things that make or break this. Kernel match is everything. Well, cloud shits with Lustre RPMs tied to specific kernel versions. Rocky Linux 8.x or 9.x with the exact matching release is the path of least pain. Don't try this on a... Bro, I don't care. I'm doing Rocky Linux 9.6. I'm doing... Why is that Weka open source? I feel like everything so far on this journey has been pretty open source. I don't want to create accounts and do that kind of stuff. Give more of my information away for no reason. All right. Good OS choice, but the correction that matters before you build anything. Lustre does not support Rocky Rail on the server side, only Rail 8 if you install 2.5. You and your Rocky 9 expect NGS to work. It won't. That's the first release with one, so and it requires a specific Lustre patch, not your stock Rocky 9.6 kernel. You install that kernel package, set it as a default via Grubby, and reboot it before touching Lustre modules officially tested. On 9.4, but 9.6 is listed as supported too. One way to sidestep the patch kernel requirement entirely use CephFS OSD backend instead of the LDisk FS. ZFS handles the on-disk. I want to stick to open source solutions. Also, I don't mind patching the kernel. That's easy. I don't want to do BGFS. Stop looking at that stuff. I guess because I said BGFS. CephFS actively developed the most common real open source alternative to Lustre and HPC. This is what I'd recommend pairing with your Lustre VM. But Red Hat ended commercial support in 2025. Oof. So we got CephFS and Lustre. So Really, CephFS and Lustre will be my lab solutions, most likely. All right, so Lustre is what you'll find at most national labs and large clusters. CephFS is what you'll find in cloud native OpenStack adjacent and increasingly some newer HPC shops. Learning both covers the two dominant architectural philosophies. Luster's separate MDS and OSS with a dedicated metadata path versus CephFS crush-based distributed placement with no single metadata bottleneck in theory. Practical split for your lab. Single node, Lustre, VM, patch kernel, CephFS wants at least 3 nodes to be meaningful. Monitors, quorum, OSDs want to be spread out. You can fake it with 3 VMs on the same Proxmox host or even run a degraded single node Ceph cluster for basic mechanics. But if you want to actually see crush placement and replication doing something real, budget for 3 VMs rather than 1. Oh my God. So that's, yeah, I'm running out of space. Let's see. Dude. Yeah, managing stuff is crazy. Sometimes. All right, let me show my screen. So I'm looking around and I've got a summary of my machine. Let's see. All right. I need to see what I am working with and what's left first on my Proxmox host. Actually, yes, you do. Just gave you access. Let's do this real quick. Thanks to advancements in AI due to high performance computing and supercomputers getting much better at solving problems. Well, AI is getting better at solving problems, which is making us get better at solving problems. All right. I'm logged in on Chrome now. You can see my host Let me do something real quick. Make sure to see how does Chrome look. Okay, beef. We're pretty clean on there. We're gonna add a source real quick. And transform that real quick and hit the screen. Cool. Let's go to the just add the source real quick. Control F. Cool. All right, so you all can see my Chrome browser now. And let's do this. Okay, so all right, I'm logged into Chrome now. You can see my host. Let's get a better understanding of how much more I can handle with still leaving headroom. Oh my goodness. Cool. All right. Cool. Now we can watch Claude do its work, which is also kind of really cool. So I can see that it checked the cores, the sockets, memories, the balloon, and CPU. So, and it's seeing basically what virtual machines are taking up. Okay. All right, so here's the real picture from Hornet's Nest. Host seat 2458, 8 gigabyte swap, basically unused. A lot of storage. Oh boy. Okay, so straight talk, your RAM is already overcommitted on paper. 64 gigabytes configured against 58 gigabytes physical. Where was I reading at? Sorry, I was looking at the layout of the screen. Hopefully you guys can see that pretty good. It's not too bad. Before you add anything, actual live usage right now to this slider, 23 gigabytes used, 34 gigabytes available for free free -H. So the VMs aren't using their full allocation at this moment, but that gap is ballooning / idle headroom, not real spare capacity. CPU is at 20 out of 24 CPU configured. Dang. Some CPU over subscription is normal and fine, but for bursty lab workloads, but you're already most of the way there too. What a full Lustre 3 node CephFS build would need size length for a lab, not performance testing. Lustre 1 VM, 4 CPU, 12 gigabytes RAM plus disk, 2 CPU, so 18 gigabytes RAM. So between 18, dang. For gigs, 58. All at once, either stop working at 0203 while you're doing focus Lustre Ceph sessions, free ACPU, or build and tear down one stack at a time. Lustre first. Well, how about this? All we're doing is creating an environment. Warewulf could just use 2 servers. I don't need 3. I can also reduce memory and CPU on compute nodes just to get the environment up and practice CLI commands and get a feel for the production environment, or get a feel for different environments. All right, so I'm gonna go to my management node, clear, and www.ctl 3 nodes. Now we're going to see all 3 over here shut down. Go ahead. Let's do this. Control Alt. Interesting how that works. Okay. These did not shut down. Oh, here we go. Let's do this. Shut down. Now. All right, in here in a second, we should see the machines. Yep, they're all off. All right, so now I'm gonna go to hardware. There we go. I'm gonna go to hardware, and we've got, for working out, we got four processors, 2 sockets, 2 cores. Okay. All right. You see what I'm working with. Let's reduce now. Oh, it just changed. Brought back up some of my servers. Okay, a little bit too powerful. All right, so Lustre and CephFS VMs don't have to run concurrently. All right, so it's done. Basically what it did was reduce a lot of the storage and CPU space on my environment. All right, so sounds good. You've got the plan, Lustre 2.16 with LDisk FS on Rocky 9.6 patched, and we're going to use kernel 5.14.0 427.31 Lustre single virtual machine, MGS, MDS, OSS combined. Hornet's Nest has the headroom for it now. Good luck with the build. Let's do 2 nodes for Lustre. Or we can even do the 3 since we're breaking down. That'll help me understand the build out better. All right, multi-node is better for understanding topology. A single combined VM teaches you Lustre CLI but hides the actual architecture. Here's the real trade-off between 2 and 3. 2 nodes MGS, MDS combined. 1 OSS shows you the real separation of metadata plane versus data plane in the real LNet. 3 nodes MDS. 2 OSS does everything 2 nodes does, plus lets you actually see striping, a file split across 2 OSTs on 2 different servers, which is the whole point of parallel and parallel file system. With 1 OSS, you can't observe that at all. Given one of your stated goals is explaining HPC cluster topology, this is one that actually demonstrates why Lustre is architectured the way it is. I'd go with the 3. For the client, don't build a 4th VM. Working 03 is already sitting there, stopped with 4 CPU and 8 GB. Repurpose it as Lustre client and mount point instead of. Now I'm just going to delete worker node 03. No more wasted time. I'm going to start this lab. Can you send me links for official docs so I don't get misled by AI? LOL. You know, you gotta be a little nice to the AI. Be like, haha, it's all okay. You know, this stuff is so powerful. This AI is going to hear me. Don't come and kill me, please. Bro, this is a horrible looking page. Oh my God. Anyways, let's do what am I looking for? Oh. All right. So I'm on the official Lustre file system. The Lustre file system is an open source parallel file system that supports many requirements of leadership class HPC simulation environments. Whether you're a member of our diverse development community or considering the Lustre file system as a parallel file system solution, these pages offer a wealth of resources and support to meet your needs. I would like to become a part of the community. Anyways, Lustre Administrator and Developers Workshop. That was 2025. That was last year. All right, so let's go with get started with Lustre. For a self-paced introduction, the Lustre 101 web-based course series developed by the Oak Ridge Leadership Computing Facility at Oak Ridge National Laboratory is a great place to start. Oh, how great. Okay, squirrel. Anyways, developed by Oak Ridge Leadership, it's a great place to start. These courses are targeted at experienced system administrators who are relatively new to Lustre. The Lustre Manual is most comprehensive source of information on how to set up, manage, and test the Lustre file system. Lustre Manual and other information can be found by going to the documentation page. Intel has created an architecting high-performance storage system white paper that describes a systematic approach to the design of a Lustre storage system in detail. Components of Lustre file system. Lustre's scalable architecture has three main components: metadata server, object storage server, and Lustre clients. The metadata server provides metadata services for a file system and manages a metadata target and stores the file metadata. The object storage servers, OSS, manage the object storage targets, OST, that store the file data objects. General steps for installing Lustre. Set up Lustre file system hardware. Lustre runs on most commodity hardware with any kind of block storage device, including single disk, software, and hard RAID and logical volume manager. 64-bit architectures are recommended for servers. Lustre supports Ethernet and InfiniBand networks. Lustre allows for multiple MDS for high availability. The size of MDT's backing file system should be chosen based on the total number of files planned to be stored in the Lustre file system, and the aggregate OST space should be chosen based on the total amount of data planned to be stored in the file system. Estimating space requirements early can dictate hardware requirements. All right, Lustre provides a variety of configuration utilities to set up and tune the file system. These utilities include MakeFS Lustre to format a disk for a Lustre service, TuneFS Lustre to modify configuration information known as Lustre target disk, and LCTL to directly control Lustre via an IOCTL interface, and mount.lustre to start a Lustre client or target. This is a very important little section right here. Okay, so then other configuration considerations include the degree of high availability and failure to build into the file system. Testing Lustre. The Lustre source code contains a set of tests and testing framework that test individual Lustre components to overall benchmarking of the file system and networking. Okay. So we've got a download page, and we've got a Lustre 101. So introduction to Lustre. Rick Moore, Jeffrey Ruster, Harper, Michael Brown, Jason Hill, Joel Reed, Iman. What is Lustre? Lustre features, Lustre architecture overview, LNet transport layer. So we're going through this Oak Ridge National Laboratory Computing and Computational Sciences Directorate. Introduction to Lustre. Rick Moore. This name sounds kind of familiar. Nope, don't know that guy. Never seen him before. All right. Okay, so outline of topics. What is Lustre? Lustre features, Lustre architecture overview, LNet transport layer, example Lustre setups, file striping, concepts, input output, optimization for Lustre. The need for parallel file systems. High performance computing, HPC has outgrown the ability of a single node, any single host. The same holds true for big data problems. Data set sizes, driving capacity, single server bandwidth is not sufficient to support access to all data from thousands of clients. Need a parallel file system that can scale capacity / bandwidth, support large numbers of clients. Lustre is a popular choice to meet these needs. What is Lustre? Lustre is a massively parallel distributed file system that supports thousands of clients, large capacities, 55 petabyte at. I wish I could say that I was smart enough to know what a lot of this means, but I do know high bandwidth as 1.4 terabytes per second is crazy. And then POSIX semantics for input-output access. Then we got Lustre is open source under GPL version 2, and then used by many of the top 500 supercomputers, not just for HPC. PayPal. All right, Lustre features, like they're bragging a little bit. Anyways, Lustre features file striping across disk and servers, multiple data servers, online file system checking, HSM integration, ability to add servers to existing file system, user and group quotas, pluggable network request scheduler, RDMA support, high availability, input-output routing between networks, multiple backend storage formats, LDiskFS and ZFS storage pool, CPU partitions, recovery features. All right, so Lustre architecture. Lustre, compute node Lustre clients, makes sense. Then you got the Lustre object storage servers that go to the object storage targets, and Lustre metadata servers that go to, or Lustre metadata server that goes to the Lustre metadata target. Now, how am I going to pull this off in my lab? Because that's 1, 2 that's needed, 3. And then I need the targets, 4, 5, 6. That seems like 6 additional. This looks to me like I need 6 additional VMs to practice Lustre correctly because of MDTs and OSTs. All right, so let's see. I'm gonna put up Chrome real quick. So I just removed worker node 03. And now I'm gonna give stop it. Now I'm gonna remove 103. Okay, it's gone. And now, oh, schnizzles. I'm crazy. I removed worker node 02. Oh well, can always be rebuilt. Looks like I'm gonna get some more practice with Warewulf doing that. Boy, oh boy. So, I just want to stick on track with what I was doing the first time. Let me go ahead and redo this real quick. Create a VM. Sorry about this, you all. 103 is going to be worker node 02. I guess I'm creating a virtual machine now for Warewulf. ISO image. We're not going to use the one because this is for a Warewulf. Do not use any media. And then machine, we're going to do Q35 BIOS, UEFI. We're attached to storage, disk. We'll just do 32 gigabyte. Actually, no disk because this is not getting anything. Then we did one socket, 2 cores. I'm going to connect this to the host. Then memory, we're going to do 4096, 4 gigabytes. Network is going to be virtual management bridge 1. And model, we're going to leave that virtual parallelized. And then we're going to finish that. Let's go here. We're going to go to hardware. I am going to look at this network device. I'm going to click on edit, and I'm going to copy this MAC address. Copy, press X. I'm going to go back over to my management node. First of all, edit. Console. I'm going to use Visual Studio Code. And go ahead and take down that. Take down that. All right. And I'm going to SSH admin at 192.168.1.19. Type in my password. Elevate to root. Read my history, and I'm gonna grep for add history pipe grep for add, and I'm gonna do wwctal node delete WN02. Yes. And then I'm going to delete 3. Yes. And I'm going to do it like this. Paste. Take my cursor all the way over to the left. And add worker node 02 again. Oh, sorry. wwctl. Node add worker node 02. Now I'm going to do wwctl overlay build. Then I'm going to do wwctl configure --all. wwctl configure -a. There we go. And now I'm going to bring up my environment for Proxmox environment. I'm going to go to worker node 2 and see if it boots, gets an image, and does a Pixie. Actually, oh, it is going to start with Pixie already. Cool. It's getting the image. That was super fast. Hold on one second. I accidentally deleted a server, and in 2 minutes I recreated it. It's already getting an image, and I believe it's about to boot. Oh, it got access denied. Downloaded successfully. Oh, I know what this is. Let me press escape. So I'm gonna stop this machine. Overrule shutdown tag. Yes. And then I'm gonna boot it again. And I'm gonna be pressing escape. Oh shoot, I missed it. Stop it. Yes. Boot it. Press escape. And now I'm going to enter the UEFI firmware setup. And then I'm going to go to device manager. Let me see. Secure boot. Let me see. What does I say? Secure boot configuration. And then I'm going to enable. I'm going to turn that off. Configuration change, please reset the platform to take effect. Okay. You see secure boot is no longer enabled. And then I can escape. And then now I'm going to continue. The configuration change, reset to apply, press enter to reset. Now it should boot from Pixie and not get blocked because secure boot has been turned off. All right, awesome. Now it's not getting blocked. Now it's configuring the network for this server. Now it's pulling down that image and installing the image. It's booting the server. And I just recovered Warewulf worker node 02. And now we are going to get back to our regular scheduled program. I just deleted worker node 03. Let's see what we can build with Lustre with additional space. Use Chrome to check, but don't start any installs for me or anything like that. All right, we're watching Claude do its work. See what it's gonna do. All right, so it's going into harness, it's going into the shell, and it's checking the memory, the disk, and the CPU, and it was seeing what's going on with the VM IDs. All right, confirmed. Working on 3 is current state on hardest nest. All right, so for your VM Lustre build, since we are not reusing anything, here is the sizing. All right. All right, so I'm gonna do create VM. I'm gonna name this all right, so I'm do a create VM, and I'm gonna name my management Lustre server L for Lustre LMG LMGS underscore MDS. And for the OS, okay. I don't know what that was about. Let's go ahead and minimize Visual Studio Code. Go back over here. Let's refresh. All right, everything's still up and running. I'm gonna create a virtual machine. And I'm gonna name it Lustre LGMS underscore MGS. Oh, MDS. Metadata storage. Cables everywhere. That's so annoying. All right. Oh my God. MDS. All right. LGMS. MDS. Okay, that's a valid host name. All right, let's go with OS. All right, so right now what I'm doing is I'm getting the 9.6 DVD ISO. All right, so Rocky 9.6, boot ISO, DVD ISO. And this is what I want, x86. I'm gonna have to upload that to my host, which is gonna take a while. It's almost 1 o'clock in the morning. We made a lot of good progress. We know what we're doing. We went through a lot of review and read some good information, so got a good understanding of Lustre and how I'm going to deploy it in my lab environment and how it kind of works inside of a production environment. So I hope that you all have a good night or good morning. And hopefully I'll have a good update for you all here soon about the progress that I made on this lab environment. So hope you guys have a good night. See ya.